Hello everyone, thank you for tuning in. My name is Ro'i, and this talk is titled on heating set generators for polynomials that vanish rarely. It's based on a joint work with Din Doron from Stanford and with Amnon Tashma from Tel Aviv. In high level, what we are going to talk about is the following. We're going to present an interesting and natural problem about polynomials that have very few zeros. Now, polynomials, of course, is such an old subject. And this is such a natural and interesting problem that it is already cool to think that this problem has been unexplored until recently. And moreover, we care about it because it's a special case of a classical problem in complexity and in pseudo-randomness that has been pointed out by Goldreich and Wigderson just recently, a few years ago. And we're going to present our results, which will be interesting and non-trivial upper bounds and lower bounds that don't match, that have a large gap between them. So this is also interesting. And we're going to see some connections of this problem to several other well-studied problems. And our starting point will be a classical problem in complexity theory, that of constructing heating set generators for polynomials. And let's go over it slowly. So our setting is that of multivariate polynomials over a finite field. So we have a field f, and we care about polynomials from f to the n to f. The input to such a polynomial is x, is n elements from the field f, and the output p of x is the sum of monomials in x. And jumping ahead, you can already see that each monomial has bounded degree, say d. And we think of n as the main asymptotic complexity parameter. So the number of variables is large and it grows, and we think of the field size and of the degree as potentially dependent on n. We will care both about small fields and about large fields. And this is, of course, a standard model of computation. We measure its complexity, for example, by the total degree, or by the individual degree, or by the sparsity, or the weight of monomials, etc., etc. And of course, it's also a ubiquitous tool in algorithm design, since polynomials with low complexity have structural features that we can understand and rely on. And our focus in this talk is on the case of polynomials with low total degree. So the total degree is bounded away from n. Say d is at most n to the 0.99. And our starting point is the following classical problem. We want to construct a small heating set for polynomials of a fixed degree d. So we want a small subset S of the domain, such that every polynomial which is non-zero and of degree at most d has some element in the heating set on which it vanishes. In other words, we want a small set S that simultaneously hits all the non-zero sets of all the polynomials of degree at most d. And let's present a visual example. So this is our domain. And for a fixed polynomial p of degree at most d, this is the set of non-zero points, the set of points on which it evaluates to non-zero. And we simultaneously consider all the subsets corresponding to all polynomials of degree at most d. And we want this red set, a very small set that simultaneously hits all of these subsets. And we think about this problem from a complexity-theoretic perspective. So we think of the complexity as getting an index I as input and outputting the ith element of a heating set. So we have a function which is called the heating set generator, h. The number of inputs to this function is called the seed length, and it directly corresponds to the size of S. And we also care about the computational complexity of h. Now, why is this problem even important? So it is a fundamental problem in complexity to construct heating set generators that are simultaneously efficient and have short seed. It's important in the context of de-randomization, since such heating set generators for weak computational models, such as polynomials, are considered to be a gradual path towards proving that BPP equals P. It's important in the context of lower bounds, since this problem is inherently tied to circuit lower bounds and to average case lower bounds for polynomials. And it's important from an algorithmic perspective, since heating set generators for polynomials are a useful technical tool in explicit constructions. So what do we know? There are two questions regarding this classical problem. The first is combinatorial. What is the best seed length that we can get? Or alternatively, equivalently, what is the smallest heating set that we can get? And the second one is algorithmic in terms of computational complexity. Can we construct efficient heating set generators with small seed? And the answer to the first question is easy. By a standard linear algebraic argument, we can show that the best seed length is essentially d times log n. This is both an upper bound by a probabilistic argument and a lower bound by this linear algebraic argument. So this is the best answer, d times log n, and we want to get it algorithmically. And the best algorithm that we know is a polynomial time heating set generator by Viola from about a decade ago, which unfortunately has seed lengths exponentially larger than the best one. It's essentially 2 to the d times log n, instead of d times log n. So there is a large exponential gap. As I mentioned before, improving the explicit construction is a hard problem that's inherently tied to circuit lower bounds and other problems, so we're trying to find other ways to make progress on it. And this is where the new question comes in. We're going to focus on a special case of this classical problem and try to make progress on it. The motivating question that underlies this work is what happens if we only want to heat those degree d polynomials that are non-zero on almost all of their inputs. Or in other words, hitting degree d polynomials that vanish extremely rarely. And intuitively, this should be an easier problem. First of all, because we're only hitting dense sets of non-zeros right now, because we only want to hit polynomials whose non-zero set is extremely large. And secondly, there are simply fewer such polynomials, so there are fewer non-zero sets to hit. So going back to our visual example, this is the domain, and now we only want to consider those polynomials whose non-zero sets are extremely dense. And you can see these are fewer subsets and they are dense. And indeed, it's a very easy problem to construct a heating set. In this example, you just put a point essentially anywhere and you get a heating set. So visually, it's an easier problem. So let's be a bit more formal. We fix two parameters, d and epsilon. D is the degree and epsilon quantifies the rarely in Vanish rarely. And we want to construct a heating set generator that hits all non-zero polynomials from f to the n to f, whose total degree is at most d, and whose maximal vanishing probability is at most epsilon. Or, more formally, the probability over a random input that p of x vanishes equals 0 is at most epsilon. And an underlying question here is, can we make further progress on top of what is already known for all degree d polynomials? And before moving on, I just want to clarify one technical point. So intuitively, you might have it in your head that by the Schwarz-Zippel lemma, all polynomials vanish rarely, because the Schwarz-Zippel lemma tells us that for every polynomial, the maximal number of zeros is d over the field size q. And there are two things to note here. The first is that we care about epsilon that is really tiny, much smaller than d over q. And for such a tiny epsilon, the problem should be really easy. Or not, we're going to see. And the second point is that we also care about settings in which the field is smaller than the degree. For example, we might care about polynomials of degree square root n over f2. And in such a case, the Schwarz-Zippel lemma does not guarantee us anything good about the vanishing probability. So really, what we have here with this tiny epsilon is a relaxation in a special case. So what do we know? Again, as before, there are two questions. One is combinatorial. What is the best seed length? What is the smallest heating set? And the other question is algorithmic. Can we match this optimal bound using an efficient algorithm? And if you recall, before we had an easy answer for the combinatorial question, and we tried to match it algorithmically. However, in this context, we do not even have an easy answer for the combinatorial question. In other words, even existentially, we don't know what is the smallest heating set. This is a great question. And indeed, this is inherently tied to the fact that in some cases, we don't even know how to count the number of polynomials that vanish rarely. And even if we know how to count them, we have no guarantee that the bound that is obtained by a probabilistic argument from counting is the best bound. So really, it's a mystery. So the two questions, to be formal, is what is the best seed length in terms of d and epsilon, and for which d and epsilon can we construct an efficient heating set generator? And why is this question important? First of all, before we even talk about complexity, this is a natural question about polynomials with few zeros that apparently hasn't been studied before, and this is already a cool starting point. And now, in randomization, this is part of a broad relaxation introduced a couple of years ago by Goldreich and Wigderson that is called quantified randomization. And this is essentially the special case of quantified randomization for polynomials. And thirdly, as you recall and as I noted before, this is a special case of a classical hard problem. We want to make progress on this hard problem. We can focus on this special case and try to make progress in it first, to try and understand what's stopping us from making progress in the general case. And lastly, while we don't have algorithmic applications so far, it's quite reasonable to expect that those will be found, considering how fundamental this subject is. Now, before mentioning our results, I want to mention several connections of the problem that we're studying to other well-studied problems. And indeed, one expects such connections to exist, considering that we're dealing with a natural problem about polynomials. So the first other problem that I want to mention is that of the weight distribution of Reed-Muller codes. And in this problem, it's a classical problem from the 60s. It calls for counting the number of degree d polynomials that vanish with probability epsilon for every possible value of epsilon. This is the weight distribution of the Reed-Muller code. And it's a classical long-standing open problem that's hard. It's fully resolved only for quadratic polynomials, and relatively recently it was resolved with asymptotic expressions only over the binary field. And note that our focus is only on the case where epsilon is tiny. So this problem is a counting problem, it's not complexity-theoretic, and it concerns every epsilon. And we care only about the case of tiny epsilon. Now, another relevant problem is that of bias versus structure in polynomials. This has received a lot of attention in the last decade and concerns with structural results for biased polynomials. So a biased polynomial is a polynomial that has too little weight for some of the output values. And via structural results that will deal with algebraic regularity and high-order Fourier analysis, we now know that such polynomials, for example, can be approximated by few polynomials of lower degree. But I want to note that our focus is again a special case. We care about biased polynomials too, but we care only about biased polynomials with a very specific pattern of bias. We care about polynomials in which a single output value has almost no weight. So again, a potentially easy special case. And lastly, this is a slide that you don't have to understand, but I do want to mention it. One could define a notion of degree d closure of a subset in f to the n, which is an analog of the Zariski closure from algebraic geometry, but in a finite sense, because this is a finite field. And we show a close connection between heating set generators for degree d polynomials that vanish rarely and small sets with a large degree d closure with respect to this notion. And you can find the details in the paper in case you're curious. And now we can state our results and contributions for the problem that we're studying. And let's set the stage for it by considering what are the interesting values for the parameter epsilon. Let's get oriented. So a random polynomial vanishes with probability 1 over q. And we denote by delta the distance of the Reed-Muller code. So we put here the point 1 minus delta. You can think of this as d over q for large fields. So why did we put this here? Well, everything to the right of 1 minus delta is only the zero polynomial, which is impossible to hit and we don't even have to consider. So this part is a part that contains only the zero polynomial. And all the way to the left, we put q to the minus d. And why did we do that? Well, by a result of warning from the 30s, a polynomial that vanishes on less than q to the minus d of its inputs does not vanish at all. So over here, what we have is only polynomials without zeros at all, which are trivial to hit. So what did we learn so far? All the way to the right, the problem is impossible, and we don't even have to consider it. And when epsilon grows smaller, we reach a random polynomial here, and when we pass the threshold of q to the minus d, the problem becomes trivial to solve. And jumping ahead, this area to the right of 1 over q will be hard, essentially as hard as the original problem. So our focus will be on the area between a random polynomial and the trivial value. So we care about epsilon that is between q to the minus 1 and q to the minus d. And we denote epsilon as q to the minus t, where t ranges from 1, which is relatively hard, or at least we will see that it is, all the way up to d, which crossing q to the minus d is already trivial. And let's state our results. I first want to state some interesting special cases to get intuition. And here we think about going all the way from the left, which is easy, to the right, which will be harder. So around the area of q to the minus d, we can construct an explicit heating set generator. Or in more detail, we construct a polynomial time computing heating set generator with non-trivial seed length, smaller than n, for degree d polynomials over f2 that vanish with probability 2 to the minus t, where t is close to d. Specifically, t is larger than d minus log n. So it's really just an additive log n term close to d. Now, think of moving on to the right. Our results do not confirm nor rule out the existence of a heating set generator with seed that is shorter than the seed for the general case of heating set generators, when epsilon is q to the minus, say, square root d. So if we only consider polynomials that vanish with probability q to the minus square root d, which is really small when you think of it, there might or might not be a heating set generator that improves on the heating set generator for all polynomials. But moving further to the right, we already have a lower bound. Specifically, we prove that there does not exist a heating set generator with noticeably shorter seed compared to the general case for degree d polynomials that vanish with probability q to the minus d to the little o of 1, say polylog d. And this is an existential result, existential lower bound. It does not depend on computational complexity. And just saying this a bit more formally, we prove two upper bounds over f2. The first is non-explicit, which we obtain by counting, appealing to a result of Kaufman, Lovett, and Porat. And the other upper bound is an explicit construction of a heating set generator that I mentioned in the previous slide. And our main result is a lower bound. This is the surprising lower bound that we just saw. It's a lower bound over fq for all q that is at most polynomial. And the thing is that there are large gaps in this slide. First, in the upper bounds, the explicit construction is exponentially worse than the non-explicit construction, the non-explicit upper bound. And our lower bound is smaller than the upper bound, even than the non-explicit one, over GF2. So this leaves a large and interesting gap of our understanding of the problem. Essentially, we get non-trivial upper bounds, explicit and non-explicit. We get a lower bound, which is non-trivial, it's our main result, and there are gaps between them, and we really don't fully understand the problem yet, which is excellent. This is a problem to consider. So let me state it a bit more formally. This will be the last slide with technical content. Recall that the optimal combinatorial seed length for all degree d polynomials is d log n. We prove a lower bound, which is combinatorial. It has nothing to do with computational complexity. It just says what is the minimum, it just lower bounds the size of any heating set of d over t. We recall that our t is such that epsilon is q to the minus t. So, for example, when t is d to the little of 1, our lower bound asserts that essentially no improvement is possible over the case of all degree d polynomials in terms of set size. But as t grows closer to d, our lower bound starts to decay. And our non-explicit upper bound gives an expression of d minus t times log n over f2. And this says that we can do better in case t is additively close to d. And our explicit polynomial time computer heating set generator is exponentially worse. It has z length 2 to the d minus t times log n. And this is where, in the previous slide, I said that if t is additively close to d up to log n, then we get something non-trivial here. Now, this might be a lot to digest, but the point is to remember that we have non-trivial lower bounds and upper bounds, and they're non-matching. And this is a natural and cool problem to consider. So thank you very much for tuning in. The takeaways that I want you to consider and to remember is that we presented a natural question about polynomials that have very few zeros, and this is a potentially tractable path to make progress on heating set generators for low-degree polynomials, and that there are interesting gaps in our understanding. The upper bounds and lower bounds currently do not match and call for additional attention. Thank you very much for tuning in. More details are available in the paper.